Let us see the quantitative measure of the tendency of an element to lose an electron is given by its ionization enthalpy. Simply say that a quantitative measurement of the tendency of an element. A quantitative, so suppose ionization enthalpy is measured, measuring of the tendency of an element to lose electron is given by its ionization enthalpy. So the ionization enthalpy is represented by specifically energy required to remove an electron. Suppose to remove an electron from the orbital or shells, some amount of energy is required. So from an isolated gaseous atom, imagine that it is X in ground state. Whereas if you take, in other words, the first ionization enthalpy for an element X is the enthalpy change delta IH. So in case for the reaction depicted in equation 3.1, I will show to you. You can see here X in grams gives rise to X plus grams plus electron loss. In case of ionization enthalpy is expressed in units of kilojoule mole inverse. So kilojoule mole inverse units for expressing ionization enthalpy in units. We can define the second ionization enthalpy as the energy required to remove the second mostly loosely bound electron in the shells of an element. So it is the energy required to carry out the reaction. So we have seen what is first enthalpy, second ionization enthalpies. If you see this graph here for zero group elements, I have taken gases like helium, neon, argon, krypton, xenon, etc. On one axis I have taken atomic number Z. Another axis I have taken you can see delta H, kilojoule mole inverse energy. So whenever, if you carefully see, helium and neon, sodium, argon, krypton and potassium. Krypton is here, rubidium is here, xenon and cesium. So here in case of variation of first ionization enthalpy delta IH with atomic number for elements Z equal to 1 to 60. It is expressed here. And energy requirement for each element. Suppose helium required this much of energy, 2500 kilo moles or kilojoule and kilojoules mole inverse of energy. Neon also almost required the 2400 or 2300 energy for losing electron from the subshells. Finally, what I am telling you, if you take this, and we have seen the first equation, and what about the second equation? X plus grams gives rise to X2 plus grams. Why? Because it is for second one, second electron, and it's a losing capacity and energy required for that, and electron is mentioned here. Energy is always required to remove electrons from an atom, hence ionization enthalpies are always positive. So energy required process, this is an energy required process, not an energy gaining process. Now in case second ionization enthalpy, second ionization enthalpy will be higher than that of first ionization, because it is more difficult to remove an electron from a positively charged ion than from a neutral atom. That is the reason why second ionization enthalpy will be higher and required. And if you take here, energy is always required to remove an electron, and the second ionization enthalpy will be higher than first ionization enthalpy, because it is very difficult to remove an electron from positively charged ion. In the similar manner, third ionization enthalpy, if you want to remove third electron from the shells of an element, the term ionization enthalpy, if not qualified, is taken as a first ionization enthalpy. Finally, if you take first ionization enthalpies of elements having atomic number up to 60, generally plotted in the graph in the figure number 3.5. In the previous slide I have shown to you, periodicity of the graph is quite striking. You will find maxima at the noble gases which have closed electron shells and a very stable electronic configurations. On the other hand, minima occur at the alkali metals and their low ionization enthalpies. Alkali metals have a, if you take a, occur at the alkali metals and their low ionization, which means alkali metals have a low ionization enthalpy. We are going to see alkali earth metals and their ionization enthalpies in the coming classes. Variation of first ionization enthalpy delta IH with atomic number for each element Z equal to 1 to 16 we have seen so far can be correlated with their high reactivity. Okay, so in addition you will notice two trends. The first ionization enthalpy generally increases, we go across a period and decreases as we designed in the group. In case these trends are illustrated in the graph figures respectively for the elements of second period and first group of periodic table, you will appreciate that ionization enthalpy, atomic radius are closely related properties. Still so far we have seen first ionization enthalpy, second ionization enthalpy, third ionization enthalpy, but ionization enthalpy and atomic radius both are correlated properties, which means related properties. To understand these trends, we have to consider two factors: the attraction of electrons towards the nucleus and the repulsion of the electrons from each other, the effective nuclear charge experienced by a specific character. Remaining part we will discuss in the coming classes. Don't forget to subscribe my videos. Thank you. Have a nice day. So, valence electron in atom will be less than the actual size on the nucleus of a shielding or screening of the valence electron. By the way, what do you mean by valency electron? Valency electron is present in outermost shells of an element or an atom. So we can say that element of an atom. Why? Because this valency electrons determines the stability and bonding capacity with other atoms. Now, for example, 2s electrons in lithium is shielded from the nucleus by the inner core of 1s electrons. Now what will happen as a result? The valency electrons experience a net positive charge. Why? Because which is less than the actual charge of +3. So in general we can say that shielding is a effective process when the orbitals in the inner shells are completely filled. Finally, this situation occurs in the case of alkali earth metals which have single outermost ns electrons by a noble gas electronic configuration. So what is noble gas electronic configuration with the outermost ns electron in case of these alkali metals? We will see in the coming topics. When we move from lithium, let us take the lithium. When we move from lithium to fluorine, what will happen, you know? So what will happen? So when you move from lithium to fluorine across the second period, successive electrons are added to the orbitals. When electrons are added to the orbitals in the same principal quantum number, and the quantum number could not be going to be changed, and the shielding of the outer nuclear charge, by the inner core of electron does not increase very much to for the increased attraction of electrons. Thus, cross a period, increasing nuclear charge outweighs the shielding. What I am telling you, whenever the nuclear charge going to be increased, automatically the process of shielding, that is also going to be increased. So far what you understood? What do you mean by shielding? Consequently, outermost electrons are held more tightly, and the ionization enthalpy increases across period. So as we go down a group, if you take an outermost electron, okay, being increases farther from nucleus, there is an increased shielding of the nuclear charge. So what I am telling you, in this case, increase in shielding outweighs increasing nuclear charge. So a removal of the outermost electron require less energy, but removal of innermost electron require more energy. Why? Because if you want to pull someone from inner to outer side, required more energy, or if you want to pull someone from outer to inner, required less energy. So in our day-to-day life. So you will also notice that the first ionization enthalpy of boron Z equal to 5 is slightly less than that of beryllium Z equal to 4. Okay. Why? Because even though the former has a greater nuclear charge, former in the sense here boron, the principal quantum number level and an s electron is attracted to the nucleus more than a p electron. Now in beryllium, electron removed, if you take electron that is removed during the ionization, s electron whatever it is there, whereas the electron removed during ionization boron is a p electron, which means electron that is present in the p shell. The penetration of 2s electron to the nucleus, okay, penetration of this nucleus to the nucleus is more than that of a 2p electron. Hence 2p electron of a boron is more shielded from the nucleus, inner core of electron, than the 2s electrons of beryllium. Therefore it is easier to remove, I already told you, the 2p electron from boron compared to the removal of a 2s electron. So which means thus boron has a smaller first ionization enthalpy than the beryllium. Another anomaly is the smaller first ionization enthalpy of oxygen compared to the nitrogen. Now this arises because in the nitrogen atom, if you carefully see, 3 2p electrons reside in different atomic orbitals, which says explained about Hund's rule. In previous classes also I made a small video upon Hund's rule. Whereas in the oxygen atom, if you take an oxygen atom, 2 of the 4 2p electrons must occupy the same 2p orbitals. Why? Because 2p electrons must occupy 2p orbitals. So this causes an increased electron-electron repulsion in between the electrons when the electrons are going to filled like that. Consequently, it is easier to remove 4th 2p electron from oxygen than it is to remove one of the 3 2p electrons from nitrogen. So electrons that are present in 4th 2p shell of oxygen, okay, consequently it is easy to remove them when compared to the 3rd 2p electrons of nitrogen. We have a problem here. First ionization enthalpy delta IH value of the 3rd period element, sodium, magnesium, silicon, are respectively 496, 737, 786 kilojoules mole inverse. predict whether the first delta H value for aluminum will be more close to 575, 760 kilojoule more inverse. Justify your answer. Solution, it will be more close to 575 kilojoule mole inverse. The value for aluminum should be lower than that of magnesium because effective shielding of 3p electrons from the nucleus by 3s electrons, electron gaining enthalpy. So as a result of it, we have seen so far what is ionization enthalpy. At ions level, enthalpy, first level of enthalpy, second level of ionization enthalpy, third level of ionization enthalpy we have seen. The remaining part we will discuss in the next video. Thank you. Have a nice day.